So let's review what we learned about circuits before the break, and then I'm going to go through an example of a complicated circuit with resistors and battery only. So just to review, in series, we're talking about resistors when they come one right after another. And when they're in series, we know that the current through the two resistors is the same. That's conservation of charge. And then to determine the equivalent resistance, so the total resistance of these two resistors, we just add them up. So this would be R1 plus R2. And that's in series. In parallel, that's when the current splits. So we have two different currents that go through these two resistors. However, the potential difference between across each resistor is the same. And then to figure it out, it's the inverse of the equivalent resistance is the sum of the inverse of the resistances. And so you set it up, this is how it looks on your equation sheet, or I think this is RP, but basically you just do this. So we add up 1 over all the resistances and then do 1 over whatever that is. Or you can do it this way. So the equivalent is the 1 over the resistances, add them up, and then take the inverse. That's what the -1 means. That means that you can also do it like this, 1 over R1 plus 1 over R2. These are equivalent. So basically, if you want to think of steps, what we'll do, instead of using Kirchhoff's law, another way to do it is to combine resistors until we only have one equivalent resistance, which is the total resistance of the circuit. And that's what I'm going to do in the example. And then we find the current or the potential difference across that one big resistor, and then we just work backwards, solving everything using these rules. Okay, so let's work through an example. So here's our circuit. So we have a 12-volt battery connected to there's 5 resistors. So it's going to split. So we have a junction here, and then it comes back together, and we have a junction here. And over here we have 2 resistors in parallel, and then a single resistor, and then this entire branch is in series, and then the entire branch is in parallel, and then we have all of these resistors. And so we'll go step by step, and we'll just start combining resistors until we get to our overall equivalent resistance, which is this one. And once we get this, then we can start solving it, and then we'll go backwards back up through our diagrams to solve for everything. Looking at this, there's a few things that we'll be using. One is when resistors are in series, remember the currents are the same, and when they're in parallel, the potential difference is the same. And then Ohm's law. So delta V is IR, which is equivalent to the current is the drop divided by the resistance. And then these are the resistances given. So we need to solve for all the currents and all the potential differences. And this is called solving the circuit. So we know everything that's going on. So what I'm going to do is I'm just going to start combining stuff together. So looking at this circuit, you can't combine this one with any of these because they're not. So I don't know, you just get a feel for it. But basically these two, we'll squeeze together first because these are 2 in series. And so 3 and 4 will squeeze together. And since they're in series, the equivalent resistance 3, 4 is just resistance 3 plus resistance 4. And resistance 3 is 4, and resistance 4 is 10. So we get an equivalent resistance of 14 ohms. So that's the resistance 3, 4. And then everything else stays the same. Okay, so now let's go to the next one. So now looking at this, still can't add this one to anything because it branches. And so we're going to combine these right here together. And these are in parallel. And that will produce resistor 2, 3, 4. So that's these 3 resistors right here. These 2 resistors. And so they're in parallel. So 1 over resistance 2, 3, 4 is going to be 1 over R3, 4. Or R2, and then plus 1 over R3, 4. So R2, 3, 4 is going to be 1 over, I forgot what R2 was, 7, plus 1 over 14. And then we'll take the inverse of that, -1. That would be 2 over 14, so we get 3 over 14. We take the inverse, so it's 14 over 3. All I did was flip it around. And that's the resistance 234. And that's approximately 4.67. So that's this resistance right here. All right, last step. Now these are all in series. So I have 3 resistors in series. I can combine them all for my total equivalent resistance. And this last resistor that I get, this is the total resistance of the circuit. So everything put together, this tells me the resistance. So that last resistance, I'm just going to say Req, instead of writing out that 1, 2, 3, 4, 5, is going to be R1 plus R2, 3, 4 plus R5. So I need R1 and R5. Let's go back up. R1 is 5 and R5 is 3. So 5 and 3. So we get 5 plus 4.67 plus 3. I think that's right. Let's go check again. 5 and 3, yeah. So that's 8, 12.67 ohm. That's the equivalent resistance of the circuit. Okay, now we can start solving it. So remember in our steps, we put everything down to one equivalent resistance and then we start solving. So the first thing that we'll do, I have the equivalent resistance. Now I can get the current going across this thing. So the current is going to be the potential difference divided by the resistance. So in this case, it's going to be the 12 volts going across this resistor. So 12 divided by 12.67. And that is 0.95. 95 amps. All right, so now we have the current that's going across this resistor. Okay, so now we can start moving back up. So we've solved everything. Oh, the potential difference across this thing is 12. Remember, it has to go back to 0 before it comes back in. So now we can go back up. So this is the current out of the battery. I'll put a B here. So if I go back up, that's the current here. And notice that these are all in series, and when they're in series, the current is the same. So I1 and I5 and I2, 3, 4, these are all the same current, which is this, 0.95. So we've already solved I1 and I5. That's going to be 0.95. So I'll go ahead and write that. So let's do it up here. So I1 equals I5, which equals 0.95 amps. Because remember, just remember, it's all the currents are the same. So it's just this last one that we have to figure. We know the current, so we can get the potential difference. I guess we can actually solve for all the potentials. You know what, I'll wait. We know the current and the resistance here, so we could actually get the potential, but I'll wait until we get up to the top to solve for that one. But we can fill it in. So 1 and 5 is 0.95. So let's go back. 0.95 amps, and 5 is 0.95 amps. Okay. Coming back here, so we know the current here, and we know the resistance. It was this. So we can find the potential difference. So the potential difference across 2, 3, 4 is going to be I times R. So we get 0.95 times the resistance, which is 4.67. Let me calculate that. So 0.95 times 4.67 4.44. So we get 4.44 volts. That's the potential difference from here to here across 2, 3, 4. We're going to use that in just a second. Okay, we're done here. So now we can move up. So now we go back to this one. So we know the potential difference from here. Remember, these two we've already solved. We just haven't calculated. We'll do it up here. We know the potential difference across these branches, and these are in parallel. So since they're in parallel, we know the potential difference across 2 is equal to the potential difference across 3, 4. And both of these are going to be equal to this one, 4.44, to the potential across delta V 2, 3, 4. So the potential across it is the potential across either of these. Because if you think, if we're coming in with, say, 10 volts and we're going to leave with 6 volts, it doesn't matter which way we go. We have to lose that 4 volts. So these two are the same, and that's why we figured out the one across here. And so we have 4.4 volts across both of these resistors, so now we can figure this out. So what we want is the current across these. So the current across 2 would be the potential divided by the resistance, 2. And the current across 3, 4 is going to be the potential divided by resistance, 3, 4. Okay, so across 2, we get the potential across 2, which is this one, the same, so 4.44, divided by the resistance, which is 7 ohms, so divided by 7. And then the current across 3, 4 is going to be 4.44, because it's the same, divided by the resistance 3, 4, which is the one we calculated, 14. So the current across 2 going to be 4.44 divided by 7, 0.63. And the current across 3, 4, 4.44 divided by 14, 0.32. All right, so now we have current 2. So let me write that in. So that's 0.63. So all we're missing is 3 and 4. But I know the current across both of them. So together, the current across each of these is, or across this little branch, is this one, the 0.32 amps. And since it's going through, they're in series, we know that this one is equal to this one. They're the same, and it's going to be this quantity, 0.32. 0.32. Now I've been rounding, so we're a little bit off, but now we can go up and we can complete everything. So notice, so what we have is across resistor 1, we have 0.95 amps. And then it comes in here and it splits. And so across R2, we get 0.63. Let me write these in. So 0.95 amps. And then it splits into 0.63. And on the other side, we have 0.32. And these two add up to be 0.95, so we're good. And then it comes back together, and the current across the last one is 0.95. It's back to what it was. And that's as expected. So it looks like we're good there. And now we can find potential difference. So we just multiply I times R, and that will tell me the potential difference. And then we'll make sure that it all adds up. So we just go down and just multiply these out, and we have it solved. So 5 times, I'm going to pause it while I'm just going to calculate all these. All right, so all I did was calculate, but now we can think about what's happening. So as we come across resistor 1, we have a drop of 4.75 volts. And then once we come into this branch, we have to go one of 2 ways. So we can come across like resistor 2, let me use red. So I'm going to go this way and then come around through this resistor and then this way. And we want to check to see if we're going to go back. So we get this one, and then we go through R2, and then we go through R5, these 3. So let me add those up. That's 4.75 plus 4.41 plus 2.85. And we get 12.01. So we have a potential difference of 12.01 volts, which is the EMF. So we're back to where we were. If we went the other way, it's going to be the same. If we add up these, it's equivalent to this one. This potential difference is equal to this one. But we have some rounding error, so we're a little bit off. But this in general is how you do it. So I know it looks really complicated, but after you do several of these, you'll figure out your own method for organizing it. But it's basically you just start working backwards. Anyway, there you go.